and the Epsilon expansion.
Okay, thank you very much. Let me, of course, start by thanking the organizers for the invitation to this wonderful conference and for the opportunity to speak here. So what I'm going to talk about is based mainly on this paper that I wrote with Igor Klebanov last September, and on a follow-up paper that should be appearing soon, also with Igor and two graduate students, Lin Fei and Grisha Tarnopolsky. So as we heard already in several talks in this meeting, a deep and interesting problem in quantum field theory is how to define a good measure of number of degrees of freedom, namely some quantity which decreases along RG flows as we go from UV to IR. And in 2 dimensions, this was famously solved by Zamolodchikov, who explicitly constructed a C function which monotonically decreases along the RG flow trajectories and is stationary at fixed points. And at the fixed points, the C function is just equal to the central charge of the CFT, which is also related to the Weyl anomaly. If we put the CFT on a curved manifold, then the trace of the stress tensor is proportional to the Ricci scalar curvature of the manifold times a coefficient, which in the standard normalizations is minus C over 12. This C is the central charge. And this can be also extracted by putting the CFT on a Euclidean 2-sphere of radius r, computing the Euclidean partition function, and taking the log. So that's the free energy on the 2-sphere, extracting the term which goes like the logarithm of the radius, gives another way to extract this coefficient. In the standard normalizations, this is minus C over 3 times log r. So in 4 dimensions, one can similarly look at Weyl anomalies. In this case, there are 2 terms in the Weyl anomaly. There are 2 coefficients A and C, which multiplies the Euler density, the 4-dimensional Euler density, and the square of the Weyl tensor. And the quantity, which is the more close analog of C in 2 dimensions, turns out to be A. In particular, we can extract A in the same way by putting the CFT on a 4-sphere and computing the Euclidean partition function. And by extracting the term which is proportional to the log r, that gives us A. Okay? And Cardy conjectured that A is the quantity that decreases along any RG flow and satisfies A in the UV is greater than A in the IR. And this was proved a few years ago by Komagorsky and Schwimmer. And it's natural to propose that the same quantity, the A anomaly, should also play the similar role in all even dimensions. In the trace anomaly, there is always a term proportional to the Euler density and several C terms in higher dimensions. In dimension 6, there is no general proof yet, but as we have heard yesterday, there is strong evidence from supersymmetric CFTs. Okay, so this was about even dimensions. Now, when we go to odd dimensions, how do we extend this theorem since there are no anomalies? So this question is physically interesting, especially in 3 dimensions where we know that there are many CFTs, and many of them are relevant to statistical mechanics and condensed matter physics. And given that in even dimension, these C functions are all constructed in terms of the partition function on the sphere, one can ask the same question and consider putting the CFT on the 3-sphere and computing the Euclidean path integral, and consider f minus log of z on the 3-sphere. Now, in a 3-dimensional CFT, there are no logarithmic divergences when you compute this quantity, and after you remove the purely power-like divergences, for example, by using standard analytic regulators like zeta function or dimensional regulator, this quantity is just some well-defined finite number which is independent of the radius. And so guided by some explicit evidence in the case of n equal to supersymmetric theories, where one can compute this quantity explicitly by localization, and also some evidence by perturbative fixed points and holography, several people suggested that it's indeed this number f, which in 3 dimensions plays the role of the C function, and it satisfies that f in the UV is always greater than f in the IR for any unitary conformal field theory. Okay, so f turns out it's also related to the universal term in the entanglement entropy across a circle of radius r in any 2+1 dimensional conformal field theory, as I think was reviewed yesterday in detail. And this connection was actually used to explicitly prove this three-dimensional F-theorem by Casini and Huerta. And there is a natural extension to all odd dimensions. One essentially constructs the same object, and there is some alternating sign structure which one needs in order to have a positive quantity which satisfies the equality in this direction. So for example, in 5 dimension it would be minus f, in 3 dimension is f, and so on. So this is just a conjecture, there is no proof of this, and it's a natural generalization to all odd dimensions. Okay, so given that there are these theorems in odd and even dimension, they are all in some way related to partition function on the spheres. One can ask whether there is some kind of natural interpolation, so unified descriptions of F-theorems and A-theorems. And the natural way to answer this question is to use the framework of dimensional continuation in field theory. Namely, we can, for a large class of CFTs, it's possible to define them in general non-integer dimension D, and one can ask what is the free energy on a sphere SD with D non-necessarily integer. And by looking at several examples in this dimensional continuation framework, in this paper last year, we proposed that a natural quantity which seems to be nice and does the job for us is to define this f tilde, which is nothing but f, the log of the partition function on SD, times this simple sign factor. Now, to understand what this sign factor does, so notice that in even dimension, when we compute this f by dimensional regularization, there is always poles, 1 over epsilon poles, and the coefficient of the residue, the coefficient of that pole is related to the A anomaly. And multiplying by this sign, which is 0 when we approach even dimension, just removes the pole and gives the anomaly. So this multiplication by sign does essentially the same job as taking the derivative with respect to log r that you would do when you work directly in even dimensions. Here we are supposed to go slightly away from even dimension, do the dimensional regularization, multiply by this, and then take the limit. That gives us the anomaly. And in odd dimensions, this definition just reproduces, this number is just plus or minus 1, and this reproduces the previous proposals that people had in odd dimensions. So then, given the known F-theorems and A-theorems in even and D dimension, it's natural to ask whether it may be that this quantity F tilde always satisfies these inequalities, and F tilde is always positive in unitary CFTs. So this would be some unified way of state the A-theorems and F-theorems in general dimensions. And before discussing some explicit examples, let me just tell you one partial answer. We indeed calculated this quantity F tilde in several examples, which can be defined in dimensional continuation, such as double trace flows in large N CFTs, slightly weakly relevant flows, and perturbative fixed points. And we always find that this inequality is indeed true. And F tilde is always positive in all unitary CFTs. And if the CFT has some non-unitary fixed point, then this inequality does not have to hold. So just a note here. So what I'm stating here is just a statement about the value of this F tilde at the fixed point. I'm not claiming that I construct a function which monotonically decreases along the RG trajectory. I'm just making a statement on the value of this number just at the CFT fixed point. So it's a weak form of F-theorem, if you want. Of course, there's nothing sacred about this factor. After we do this, we can multiply it by any positive function of dimension that will still do the same job. This is just conventional so that in odd dimension, it gives the F that people used in previous work. OK, so to get a feeling of how this works, we can first look at free fields. So consider, for example, a free conformal scalar field in dimension D. Then F for such a field is just a free theory. You just have the log of the determinant of the kinetic operator, and there is this conformal coupling term which comes from the coupling to the curvature. I'm setting the radius to 1 here. And if one computes these determinants, after some work, it can be shown that it can be cast into this relatively simple form as an integral, which is valid in any dimension. And here we see that there is the appearance of this factor. And this was actually the first hint that it may be a good idea to multiply by this sign factor. So as I said before, one can see that if you expand this quantity near even dimension, then you get poles. That just comes from this sign here. And the coefficient of the pole gives the A anomaly. So for example, in 4 minus epsilon dimension, this gives 1 over 90 epsilon, which is the A anomaly coefficient of a scalar in 4 dimension, and so on. This formula reproduces all known anomalies in even dimensions. So after we go to this f tilde by removing this factor, we get this function, which is now always positive for all dimensions and smoothly interpolates between the values of f for the free conformal scalar in odd dimensions and the A anomaly coefficients. So I'm sorry, the font here is a little small, but this is a plot of this quantity f tilde in dimension between 2 and 6. And these simpler values are the A anomaly coefficients, and these more complicated looking values that involves log 2 and zetas are the values of f in odd dimensions. So we see here that in terms of f tilde, they are basically on a very similar footing. There is an explicit interpolating analytic function that join them together. So anomalies in even dimension and f values in odd dimension, which are not related to anomalies, they can still be put on the same analytic smooth function. Okay, so as an example of interacting fixed point, we can consider, for example, a general CFT with a large n expansion and perturb it by a double trace operator. So here O delta is a single trace operator in the unperturbed CFT. We add the square of it. And when this perturbation is relevant, which means that delta is less than d over 2, then one can show by large n techniques that there is a RG flow from the unperturbed CFT in the UV to a new CFT in the IR, where the dimension of this operator has gone from delta to d minus delta plus 1 over n correction. And of course, this is a story which is well understood also in ADS CFT, where the dual of this flow just corresponds to changing boundary condition for the scalar field, which is dual to this operator in ADS. And the change in the sphere free energy for this kind of flow to leading order in large n is explicitly computable. I'm not going into the detail, but what it turns out is that it's simply given by the log of the determinant of the 2-point function of this operator in the unperturbed CFT on the sphere. And this 2-point function on the sphere is just fixed by conformal invariance. This Sx or y is just the chordal distance on the sphere. You can expand this in harmonics and compute this determinant. And you get, again, some simple integral formula. And you see, again, that there is this sign factor showing up here. And this is some universal formula for the change in delta f, which only depends on the dimension of the perturbing operator. It doesn't depend on the details of the unperturbed CFT. So in terms of f tilde, again, we get a very nice function of delta. And we can see explicitly from this integral that if delta is above the unitarity bound, and also we are assuming that delta is less than d over 2, so that we have a relevant perturbation, then this integral is actually negative, which means that because this delta f is f IR minus f UV, it means that indeed we have shown that f tilde in the UV is greater than f tilde in the IR. And this works for any double trace flows at large n, provided provided the unitarity bound is satisfied on this delta. And a completely analogous calculation also works to the large n UV fixed points that arise when this perturbation is irrelevant. So delta is less than d over 2, but delta is below d over 2 plus 1, so that the fixed point is still unitary. So an explicit example of this is the three-dimensional critical Gros-Nouveau model that was discussed this morning, where this double trace perturbation is just a psi bar psi square operator. And the dimension of that operator lies in this range in d equal 3, and more generally in the whole range between 2 and 4. Another example of this kind of UV fixed points, which is less well known and it's more exotic, but was also discussed this morning in the review, is this case of the interacting ON models in dimensions between 4 and 6. So if we start with the standard action for the ON model with quartic interaction, and we know that this interaction is irrelevant above 4 dimensions, so the theory is trivial in the IR. But one can show by Largen methods, and I think this was first shown by Parisi in 75, that this model has unitary UV fixed points if dimension is between 4 and 6, which are well defined to all orders in 1/n expansion. Now, what happens at finite n, whether these fixed points are really well defined, is more complicated. I'm going to discuss here. I just want to use these fixed points to test this F-theorem for the purpose of this talk. These fixed points also play a role in the higher spin CFT dualities. So, of course, the physical dimension here is d equal 5. And that in d equal 5, these Largen UV fixed points are supposed to be dual to the Vasiljev higher spin gravity in ADS6, where one chooses non-standard boundary conditions on the bulk scalar. So recently we proposed that this same UV fixed points of this quartic model can actually be reached from another model in dimension between 4 and 6, which is a model with n+1 scalars and cubic interaction. So the claim is that you can reach this ON interacting theories in dimension between 4 and 6 either by flowing from a theory of n+1 scalars by adding these relevant cubic perturbations and going down to the IR, or you can view it as the UV fixed points of this quartic theory. So this description in terms of cubic interactions is perturbative near the upper critical dimension. So in 6 minus epsilon dimension, you can do perturbation theory. And you can check that these fixed points are unitary perturbatively, at least for sufficiently large n. Okay, so but as I said, for the purpose of this talk, I just want to use these models to test the F-theorem. And the fact that we have two descriptions gives a non-trivial check because we have two inequalities to satisfy. We can flow, as I said, we can flow to the same critical theory either from the theory of n+1 free scalars in the UV by adding relevant perturbations, so that gives this side of the inequality. But we can also view this as the UV fixed points of the quartic theory, which means that we can perturb this and flow down to free n scalars. So we have two inequalities to satisfy. If we look at d equal 5, then we can compute this very explicitly at large n. F at the critical point is equal to the free contribution plus this number. And then one can see that this side of the inequality is satisfied because this is positive. But this is just a special example of the general proof for double trace flows that I discussed earlier. What is less trivial is to show that this side is satisfied, because this depends on the specific numbers that are involved here. So this number is given here. And it turns out that this happens to be smaller than the value of f for a free conformal scalar field in 5 dimensions, which is given by this. And it's smaller not by much. It's just a factor of 3 or 4 between the two. So this gives a non-trivial test that indeed both inequalities are unsatisfied in d equal 5. So this is an explicit test, at least in the Largen expansion, of the 5-dimensional F-theorem. And more generally, one can do this calculation using the dimensional continuation that I described before in the full range between 4 and 6 dimensions. And these inequalities are always satisfied there, and they are not satisfied outside this range where these fixed points becomes non-unitary. So another example of flows that we can study in any CFTs quite generally are flows which are triggered by slightly relevant operators. So this is not necessarily large n. We just have some CFT with some operator which has dimension slightly below the marginal. So delta is d minus epsilon with epsilon much less than 1. And if we deform the CFT by such an operator where this GB is some bare coupling constant of dimension epsilon, then there is a flow to an IR fixed point. And this can be studied in conformal perturbation theory. As usual, one can introduce a renormalized coupling constant, dimensionless coupling constant G. And there is a beta function, which one can compute explicitly. And the leading term is just a universal term, which does not depend on details. It just depends on this number C, which is the ratio of the 3-point function coefficient over the 2-point function coefficient. Of course, I could set this C2 to 1, but I'm not doing it here. So then one can see that there is a IR fixed point where G is of order epsilon, and this is the IR fixed point. And so this fixed point is the IR fixed point that you reach after you follow this flow triggered by this slightly relevant operator. And to compute F on the sphere, we just conformally map, we do conformal perturbation theory and conformally map the 2-point function, 3-point functions to the sphere. And so this is what you get to leading order, where these I2 and I3 are these integrals on the sphere of the 2-point function and the 3-point function, where S is the chordal distance, again, on the sphere. This can be computed very explicitly. They were computed first by Cardi several years ago. And then one gets a simple answer for the change in the free energy under this RG flow triggered by slightly relevant operators. And in terms of f tilde, after removing this sign factor, the answer is quite simple. There is some positive factor in front, and this function here, which turns out to be just the integral of the beta function. So remarkably, this is just determined by some flat space data, which are the beta function and C2, even though we have to go to the sphere to do this calculation first. And if you then set G to the fixed point, you get this explicit result. And you can see that for unitary CFTs, where C2 is positive and C is real, the generalized F-theorem in all dimensions indeed works. And so this calculation generalizes to all dimensions, previous computations that was done in odd D and even dimension, but they were done in slightly different ways. And here, using this F tilde, we can do them all together in a kind of unified way. Okay, so now, well, it's interesting to have this interpolation, I think, between A and F theorems. You can ask if this dimensional continuation is actually useful to learn something about the CFTs in the physical integer dimensions, because that's what we are interested in after all. But there is one natural thing that this is useful for, which is just using the Wilson-Fisher epsilon expansion, and in the same way as it was used for estimating critical exponents in CFTs, we can use it to estimate what is the value of F for some interesting CFTs in the physical dimension where we don't know how to compute it directly. So for example, we can consider a 3-dimensional Ising model, or more generally ON models in 3 dimensions. These are strongly coupled CFTs, but they are weakly coupled if we go to 4 minus epsilon dimension, as is well known, right? So here is a brief review. If we consider the quartic field theory in 4 minus epsilon dimension, then there is a perturbative beta function and a perturbative fixed point. And n equal 1, epsilon equal 1 correspond to the 3D Ising model. N equal 1, epsilon equal to 2 would correspond to the 2-dimensional Ising CFT with central charge 1/2. So for critical exponents, this epsilon expansion has provided quite good results, estimates for the operator dimensions, provided you use some kind of resummation technique to resum these epsilon expansions. So now we want to do a similar thing for the sphere. Now the actual detail of the calculations, if we want to do this to relatively high order in epsilon, are complicated. So let me just go through this quickly. One is to learn how to renormalize these theories consistently in curved space, and this was outlined in the 80s by Brown, Collins, and Hattrell. So what you have to do in curved space to renormalize the theory consistently is adding curvature terms for all possible terms which are dimensionless in D equal 4. And then, so these terms are, of course, the square of the Weyl tensor, the Euler density, and this H is just basically the Ricci scalar. It's just a convention used in the literature. And then there is also a term for the coupling of the scalar to the curvature, which I have separated here from the usual conformal coupling. So this action depends not just on the lambda parameter, but also on these other parameters, which should be regarded as extra couplings in the theory. And one can renormalize it. You can express these bare couplings in terms of renormalized ones. And after you do that, the free energy is finite. But the price is that, as usual, the renormalized coupling have a beta function. And then the free energy is a function of all the renormalized coupling and of the renormalization scale. And it satisfies some Kalan-Simansky equation. And then one can see from this equation that if you want to reach the fixed point in 4 minus epsilon dimension in curved space, you you not only have to set the beta function of the coupling to 0, the lambda coupling, but also all the curvature couplings. And once you do this, once you set all couplings to their fixed points, you get just a function of epsilon, which is a well-defined number independent of the radius. Okay, so let me spare you the details. We did this up to 6 loops, and this is the result that you get in the end, up to order epsilon to the 5. Of course, the numbers are not important, but it's remarkable that it's relatively simple. It's just rational numbers up to zeta 3 that start appearing at order epsilon to the 5. Once we have this, we can try to resum it using some techniques. The simple-minded one is just to use a Padé approximation. So make an ansatz like a rational derivation of 2 polynomials. And this kind of Padé approximations can be improved a lot if we impose that when epsilon become 2, which is 2 dimensions, this F should reproduce the central charge of the 2-dimensional Ising model, which is exactly known to be 1/2. And if we impose that as a condition, we can improve our estimates considerably. And here is the plot of the result. So this is the ratio of F for the Ising model over F for the free scalar, in dimension between 2 and 4. The dashed line is just the prediction of the epsilon expansion without any resummation, which is given here. That's already quite good. It goes close to 1/2 in 2 dimension. And the continuous line is the Padé approximation. So using this technique, we get an estimate, a prediction for what F is in the 3-dimensional Ising model. It's given here. We get that the ratio of F in the 3-dimensional Ising model over free scalar is about 0.97. So, well, notice that this is below 1 in the whole range, consistently with this F-theorem, because we reach the Ising model in the IR by perturbing the free scalar. And this number, surprisingly, is very close to the free field value. It's just a few % below. And this actually is qualitatively similar to what was found for CT using conformal bootstrap approach. So CT is also a measure of degrees of freedom, so it makes sense that it gives a similar estimate. And in that case, they find that the ratio is about 0.95. And as we have seen in the talk of Sasha, there are several quantities in this Ising model that seems to be close to free field value, even though the theory itself is strongly coupled. Not all quantities are close to free field values. It would be nice to understand this better, maybe, and why this is so close to being the free field value. So let me just conclude and summarize. So we studied dimensional continuation of the sphere free energy and provided some evidence for a unified description of F-theorems and A-theorems in continuous dimensions. The quantity that we find useful is this quantity F-tilde, defined in terms of this sign factor. Multiplication by this sign factor makes this quantity very smooth. It's always positive. It doesn't have any pole. And the fact that it's smooth makes it very useful to use Wilson-Fisher epsilon expansion to predict values of F for interesting CFTs. And we have a prediction for the 3D Ising model where this F is just a few % below the free conformal scalar. And it would be interesting if this could be checked by some other methods, for example, by some numerical calculation of the entanglement entropy for the 3-dimensional Ising model, which for a for a circular geometry should be exactly equal to this F. Okay, I will stop here. Thank you.
Thank you very much. Are there questions or comments? Yes.
So you mentioned in 5 dimensions a critical model tool to Vasiliev, and in 3 dimensions it admits a parity-breaking deformation, which is dual to Chern-Simons. Is a parity-breaking deformation in 5 dimension, and what is its microscopical interpretation?
Well, this is not, it's not been studied very much, but of course you can think about adding a 5-dimensional Chern-Simons term. But on the Vasiliev theory side, it's not known whether there are parity-breaking extensions of the 5-dimensional, of the 6-dimensional Vasiliev equations. There probably are, but it's not known.
To follow up on that, I think adding a 5-dimensional Chern-Simons term would be a big change of the bulk theory, because it adds new degrees of freedom. The 5-dimensional Chern-Simons equation of motion doesn't set the gauge field to be pure gauge. So it would add new degrees of freedom, so presumably new bulk fields. So I don't think gauging with respect to 5-dimensional Chern-Simons is a small deformation of the ungauged theory.
More questions?
Is there a way to think about the sin pi d by 2 factor that you added in holography?
Yes, I think one can see that that's also natural there. Basically, when you do the calculation in holography, you always get some overall factor of the regularized volume of ADS d plus 1. And you can see that if you multiply that by this sign factor, you just get a positive smooth function of dimensions. So yeah, so you can see that that does the same job there.
Okay, thank you very much.